Selective precipitation is where we add a reagent that will precipitate one of the cations that are in the solution, but not the others. And so we can separate that one out and identify that it's there. The reagent would be chosen based on KSP values. You want something that's going to precipitate most of it. So we want a difference in KSP values between the one that precipitates and the ones that don't precipitate. We want a factor of at least 10 to the third. And we can identify what concentration is needed to trigger precipitation by comparing Q with KSP. So if Q is smaller than KSP, then precipitation will occur, right? So here's an example. The magnesium and calcium ions present in a solution can be separated by selective precipitation with potassium hydroxide. What minimum hydroxide concentration triggers the precipitation of the manganese ion? And we're given KSP values for magnesium hydroxide and for calcium hydroxide. So the KSP for magnesium hydroxide is significantly smaller than for the calcium, right? So we can precipitate magnesium without getting the calcium. So what is the minimum hydroxide ion concentration? Well, let's look at the equation. So KSP, the solubility product constant, we look at the compound as a solid, and we were thinking about it dissolving. So that's going to form magnesium ions and 2 hydroxide ions. So KSP is going to be equal to the magnesium ion concentration times the hydroxide ion concentration squared, right? So we want to know what is the smallest hydroxide ion concentration that will give us precipitation. I think I said that backwards earlier. If Q is larger than K, you'll get precipitation. If Q is smaller, it will dissolve. That was backwards. Well, these are going to be the equilibrium concentrations, right? So we know that the magnesium ion concentration is 0.025 molar, and we know what KSP is. So we could calculate the hydroxide ion concentration at equilibrium, right? And if we went above that, it would precipitate. Does that make sense? So let's calculate the equilibrium concentration of hydroxide ion. So that's going to be KSP divided by magnesium ion concentration, and we need the square root because this was squared. So I took KSP, I divided by this, and I took the square root to get rid of the square. And so KSP is 2.06 times 10 to the minus 13, dividing by the magnesium ion concentration, 0.025, and the square root. So 2.871 times 10 to the minus 6 molar. Yeah.
So you chose the magnesium because instead of the calcium one because it has a smaller KSP?
Yeah, magnesium has a smaller KSP, which means it's less soluble. So magnesium will precipitate first because it's less soluble in the presence of hydroxide. Also, the question asks me for magnesium.
Okay.
If you put more hydroxide in, you'll precipitate more magnesium, and eventually you'll precipitate the calcium as well.
So the question always clarify which one to use?
It won't necessarily. I mean, we should be able to look at the KSPs and tell which one's going to precipitate first. The one that's the least soluble, smallest KSP, will precipitate first. Let's do another one. A solution is 0.085 molar in lead-2 ion and 0.025 molar in silver ion. If selective precipitation is to be achieved using sodium chloride, what minimum concentration of NaCl do you need to begin to precipitate the ion that precipitates first? And then, what's the concentration of each ion left in solution at the point where the second ion begins to precipitate? And we're given KSP values for both of the compounds, lead chloride and silver chloride. Okay, so which ion is going to precipitate first? The silver chloride, because its KSP is smaller. It's less soluble than lead chloride. So the silver chloride will precipitate first. Part A is asking, what is the minimum concentration of sodium chloride to begin precipitating the silver? So silver chloride dissolving makes silver ions and chloride ions. You don't necessarily have to write out the equation, but you need to think about it because in the last one, there were 2 hydroxides, and that affects the equilibrium constant expression. KSP for this is equal to the silver ion times the chloride ion, and that's equal to 1.77 times 10 to the minus 10. So we'll calculate the chloride ion concentration at equilibrium, and we know that as soon as we get past that, the silver will begin to precipitate. So the chloride ion concentration will just be equal to KSP divided by the silver ion concentration, which was given, 0.025. So 7.1 times 10 to the minus 9. Any questions about that part? What's the concentration of each ion left in solution at the point where the second ion begins to precipitate? Well, what chloride concentration do we need in order for the lead to begin to precipitate? We need to calculate it, right? Similar calculation. We've got 2 chlorides. All right, so KSP here is equal to the lead concentration times the chloride concentration squared. So if we calculate the chloride ion concentration when the lead begins to precipitate, that's going to be KSP for the lead, 1.17 times 10 to the minus 5, divided by the lead concentration. And we have to take the square root of that. So 1.17, bless you. It's a new number, 1.17, bless you, times 10 to the minus 2. So you have to get to a higher chloride ion concentration. Bless you. So at the point where the second ion, the lead ion, begins to precipitate, what's the concentration of the second ion? Where it's just going to start precipitating. We haven't precipitated any of it yet. It's the same, right? It's going to be this concentration. We're ignoring any changes in volume. So at that point, the lead ion is going to still be its original concentration because it hasn't begun to precipitate yet. We need to figure out what the concentration of, well, we did the concentration of chloride. We need to figure out what's the concentration of the silver ion now. So I'm going to erase some things over here. So I may regret that, but and let's make an ice table. So let's put in this for the concentration of the chloride. So that would be, get rid of the scientific notation. So 0.00117 molar, and this is 0.025 molar. And that would be the initial. And the change, they're both going to go down by the same amount, right? And then at equilibrium, we're going to have 0.025 minus x and 0.00117 minus x. Nah, this isn't the right way to go about it. Can you see what's going to happen here? How does this concentration compare to the concentration of silver ion? It's smaller, right? So if I'm saying this is the concentration where the lead begins to precipitate, then I can't be changing that. And I can't do x is small here because then x is really small for that one. So this isn't going to work. So what else can we do? Well, let's think about what happens without numbers. So we're adding chloride, and at first nothing happens. And when we get to that first level that I erased, we begin to precipitate the silver. And as we continue adding more chloride ion, more silver ion precipitates, and the chloride concentration really doesn't change much, right? Because it's being precipitated. At some point, though, we're going to have precipitated most of the silver ion, And then the chloride ion concentration can go up. So we've added chloride. I think what we need to do is just put this concentration in for the chloride and calculate what the equilibrium concentration of this is using KSP. Can you tell I didn't read my slides before class today? That was a bad idea. No, not that one. We're calculating silver. Silver ion concentration will be KSP divided by the chloride ion concentration. 1.77 times 10 to the minus 10 divided by...
Wait. Are you using that one? The times 10 to the minus 2? Or?
I'm using the one for silver.
Oh, from there, okay.
Yeah.
Sorry.
And that's okay. It's a lot of 1s and 7s. I'm a little confused myself. 1.77 times 10 to the minus 10 divided by 1.173 times 10 to the minus 2. This is giving me 1.5 times 10 to the minus 8. So that's the concentration of the silver ion. This is the lead ion. And here's the chloride ion. Sorry, that's messy. It's crazy messy. Any questions?
So we don't have to add the chloride concentrations from the...
Well, you're not going to add chloride concentrations because it's in the same solution.
Okay.
So the chloride ion concentration is the same throughout the solution.
So the first equation we did was just to answer what it would be.
Yeah, so part A was, what's the chloride ion concentration when things start to precipitate? And what they don't ask, just, there's another ion in that solution, isn't there? Sodium. They don't ask that, which is fine because we don't really want to answer that, do we? No, we don't. Any other questions?